Okay, hi guys. So in this lecture, we'll be continuing on seeing bond energy, and later we'll be seeing photochemical reactions as well. So let's continue. So in the previous lecture, we actually started off with um, some definitions of enthalpy and seeing when the energy is absorbed and what would be the sign of delta H in case of absorption or release of energy. So in this lecture, we'll be continuing on seeing that. So bond energy is this energy required to break 1 mole of bond of given molecules. So this is nothing but energy required to break 1 mole bond of given molecules. Okay, so let's say we have a ClCl or Cl2 gas. In order to break into 2 Cl atoms, we need, let's say, x kilojoule, where x is positive. Okay, and again these two Cl atoms again form ClCl or Cl2 gas. So in this case, energy would be released, that would be just the negative of bond energy which is required to break the bond. Hence x kilojoule energy is released when Cl2 is formed. In other words, I can write this as x kilojoule energy release when 1 mole of Cl2 is formed. Cl2G is formed. Okay, so please remember that these things are only applicable in gaseous phase, applicable in gaseous state. Okay, next let's see photochemical reactions. Okay, so reactions that take place in presence of light are called photochemical reactions. Reactions taking place in presence of light are called photochemical reactions. Okay, so let's see an example. We have HBr, which again on passing in presence of H nu sunlight will have hydrogen atom and bromine atom, which are free atoms. Okay, and again if we have a Cl2 gas, so Cl bond will cleave and will have 2 Cl free atoms. Okay, so energy required for this to take place is Hc by lambda, but this energy is just for one molecule of the respective, or rather for the respective molecule. This is just for one molecule. Energy is required to break it. We can calculate for 1 mole from this. Okay, and hence for calculating of bond energy, for 1 mole it would be just multiply energy into this energy into Na. Okay, or the Avogadro number. So you will have total number of, or rather total energy required to break 1 mole of a molecule would be this kilojoule per mole. Okay, now let's look into definition of quantum yield. So quantum yield is the number of moles of reactant consumed divided by number of moles of photons absorbed. So number of moles of reactant consumed divided by number of moles of photons absorbed is the quantum yield. Okay, we can also denote it with phi. So phi would be nothing but number of molecules of reactants consumed. We can also write it in terms of molecules divided by number of photons absorbed. Okay, so just remember this form. Okay, so let's actually do some quick practice on it. So you have to calculate maximum wavelength in angstrom. In angstrom of a photon that can dissociate x2 molecule into gaseous atoms. Okay, you have been given that delta H equals to binding energy of x2 gas is 39.6 kilojoule per mole. Okay, so you have to calculate the wavelength. So obviously energy equals to Hc by lambda. Please remember that we are just talking about a molecule. So energy is already given to you, 39.6 kilojoule per mole, or 39.6 into 10 power 3. Okay, so this is already 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8, which is Hc. Okay, and then divided by lambda. Okay, or so this is kilojoule per mole. Is actually, we saw that we have to dissociate a molecule. You have to find the maximum wavelength for dissociating a x2 molecule, whereas in you have been given delta H, and delta H is always calculated per mole as written here. Okay, so you have to multiply it with Avogadro number as well. Okay, so multiply it with Na. Okay, and after multiplication of with Na, you will get so this is already in kilojoule per mole, so no need to multiply it with 10 to the power 3, because we saw here that it is directly in kilojoule per mole, so no need to multiply it with any, so no need to convert it into joules. Kilojoule per mole is a correct unit. 6.6 into 10 to the power minus 34, which is Hc by lambda multiplied by Avogadro number, which is 6 into 10 to the power 23. So you can calculate the value of lambda from this. Okay, so next, coming to the next question, you have been given that the electromagnetic radiation, so you have to calculate the energy of radiation of lambda equals to 242 nanometer is just sufficient to ionize an A atom Okay, and you have to calculate what is the activation energy or rather ionization energy of Na in kilojoule per mole. Activation energy of Na in kilojoule per mole. Okay, so you have been passing a electromagnetic radiation of lambda equals to 242 nanometer, and you have to calculate. So this energy is actually just sufficient to ionize the Na atom. Then you have to calculate the ionization energy of sodium. So we know that energy which is required would be Hc by lambda multiplied with Avogadro number. This will give me the binding energy or the ionization energy. So H is, I can put the values in place. C, lambda is 242 newtons per minus 9, and then you have been given that it is multiplied with 6 newtons per 23, or what is Na, which is Na. So one way of calculating that is this, and another could be, you can just write energy as 1240 upon lambda electron volt per atom. We have actually seen this form in past lectures, so if you remember it, you can directly use this. Okay, so this is per atom. So for a 1 mole or in kilojoule per mole, you have to multiply it with Avogadro number, so it's just 242 here. So charge on electron is 1.6 × 10⁻⁻19. So I hope this lambda, you remember that we took it in nanometer, so no need to replace or no need to add any 10th exponential power. So it is correct, so as it is 242 in nanometers itself. So electron volt and number of atoms, so number of moles or other in kilojoule per mole you have to calculate. So it is per atom, and there are 6 newtons per 23 atoms in a mole. Okay, so just multiply it with 6 newtons per 23, so it would be kilojoule per mole. Okay, so for converting it into kilojoule, you have to again divide it with a factor of 1000, because this would be in joules. So to convert it into kilojoule per mole, just divide it with the 1000. Okay, so because electron volt would be equal to joule, okay, not kilojoule. So for converting this value which is in joule, you have to divide it with the 1000 with a factor of 1000. So now you can calculate the answer, and the answer should come out to be 4900 kilojoule per mole. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing isotopes, isobars and things like that. So till then, good luck and goodbye.